So there are four general laws that relate to the four basic characteristic properties of gases to each other, right? And the ones that I'm referring to is Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Now we'll take a look at some examples, but before that, I want to talk a bit more specifically about each type of law. So with Charles' law, it states or it gives us the relationship between volume and temperature, and if the pressure and the amount of gas are held constant, right? So first, if we know that in the temperature in Kelvin of a gas is increased, then the volume of the gas will increase. And then on the contrary, if the temperature again in Kelvin of the gas is decreased, then the volume of the gas will also decrease. Right? So temperature and volume are proportional. If one decreases, the other decreases. If temperature increases, then the volume will increase. Now, Boyle's law states that the volume of a given amount of gas is held at a constant temperature varies inversely with the applied pressure when the temperature and mass again are held constant. If pressure increases, volume will decrease. If pressure decreases, volume will increase, right? We see that inverse relationship, which is contrary to Charles' law, which states that temperature and pressure have a direct proportional relationship. Avogadro's law gives the relationship between the volume of the amount of gas in moles when pressure and temperature are held constant. Take for instance, if the amount of gas in a container is increased, the volume will increase. Right? If the amount of gas in a container is to decrease, then again the volume will decrease. This is assuming again that the container has expandable walls, right, like a soccer ball. Again, this Avogadro's law is similar to Charles' law in that they state direct proportional relationships. But with Avogadro's, right, it's the volume and the amount of moles, right? More moles, the more the volume increases. While with Charles' law, right, the higher the temperature, the the greater the volume, uh, and vice versa, right? If we see a decrease in the amount of moles, we see a decrease in volume. If we see a decrease in temperature, we see a decrease in the amount of pressure. Now, with Gay-Lussac's law, it states that the pressure of a given amount of gas held at a constant volume is directly proportional to temperature, again in Kelvin temperature. So, take for instance, if you heat a gas, you give the molecules much more energy, and because they have much more energy, they're moving a lot more rapidly. Because they're moving a lot more rapidly, this means that there's going to be more impacts on the walls of the container, which will therefore increase the pressure within the container. However, if you were to cool the molecules down, then you'll see a difference in the movement, right? Now, rather than moving fast, they're going to be slowing down, and therefore the pressure will decrease. Okay, so with this in mind, now let's take into consideration three components of the kinetic molecular theory. So we want to discuss a bit more about gas specifically. So I want to make 3 points about the kinetic molecular theory. So we'll make 3 bullet points. So the first point is that gases have no definite or fixed volume or shapes. And then the second point I want to make is that gases have more kinetic energy compared to solids and liquids. And then the last point I want to make is that gases are compressible. So if you put them in any container, gases will take on that shape they are placed in. Now that we have now that we have understood the three components of the kinetic molecular theory and that we understand the four different gas laws, let's look at some examples. Okay, so in this example, we're told that a sample of gas at standard pressure is compressed to a smaller volume. What would happen to the pressure of the system? Assume all other variables are held constant. So here we understand that our standard pressure is being compressed, right? And as a result of the standard pressure being compressed, we understand that the volume is getting smaller. And if we go back to the beginning of this video, right, we mentioned a specific law that talks about pressure and volume, and that's Boyle's law. All right, so we understand that in this specific example, Boyle's law is being applied because pressure is being compressed into a smaller volume. And as a result of this compression, the pressure of the system will increase. Again, this is due to this inverse relationship. A smaller volume would allow for more collisions and thus more reactions. So here, let's draw this out. So if we do a before and if we do an after. So we understand that the standard pressure is being compressed due to a smaller volume, right? So we would have a bigger container here in our before and then a smaller container. Now, we want to make sure, again, that we retain the law of conservation of mass. So with that in mind, right, we want to make sure that the amount of atoms we add before and after remains the same. So here before, right, we'll add 3 atoms. So we can add 1 here, right, and it makes a collision with this wall and it bounces off. Right, and then we have another one here. And it goes there, right? Again, the direction doesn't matter. It just shows you that these atoms are bouncing off, right? Here's before, and then as a result of the volume getting smaller, right, the pressure is going to want to increase, right? Because now these atoms are making more collisions with the wall. And we do another one. In our after, right? In our after, it looks a bit more chaotic, right? We see that these atoms are bouncing a lot more from the walls. Well, before it's a lot more clear. You can see you can generally understand the direction where these atoms are headed to, right? And from this understanding, we understand that Boyle's law states that when your volume decreases, when you have a smaller container, and your pressure compresses, you understand that as a result of that, your pressure in the system will increase. And this makes sense because if we have the same amount of atoms, we have the same amount of mass, and if we just decrease the volume, then the pressure of those atoms, they want to escape. And because they want to escape, it's going to expand the volume, although it would be stuck in that shape. It would be stuck in the container that it's placed in. And it causes more collisions with the wall, and therefore it causes greater pressure. Okay, let's take a look at another example. So this next example states, people who are angry sometimes say that they feel as if they're going to explode. What will happen to the volume of a person's lungs if their body temperature rises and the pressure of the number of moles of air in their lungs remain constant? So, okay, so we know the number of lungs is remaining constant, and we know the two other factors are changing, and that is temperature is changing and the volume is changing. So these two variables hint at Charles' law. We understand that Charles' law is being applied here. And we understand that because if a person's body temperature rises, then the volume of the person's lungs will increase. And this is due to temperature and volume having this direct relationship, as Charles mentions. And because again, temperature as temperature increases, it leads to more motion and more collisions with more collisions from these atoms. And let's draw a particle diagram. So again, if we have a before and then an after. So we know that the volume of the person's lungs will increase. Before, right, we see that temperature is increasing. All right, so this is going to cause a lot of collisions, right? Because these particles are going to want to move fast as a result of the increased temperature. And for this one, we'll just draw 3 particles, right? And as a result of this high temperature, this is going to expand the volume, right? This is expanding the volume due to the rise in temperature. From Charles' law, we understand that the volume of a gas is directly proportional to its temperature. So if you think about it this way, right? So if you increase the volume of a gas, it must keep the pressure constant. And the only way to achieve this constant pressure is for the temperature of the gas to increase as well. Okay. Let's move on to one last example. This next example states that you're going to a park and you notice that your soccer ball is flat. So you want to add more gas using an air pump. What will happen to the volume of this soccer ball, assuming that all other variables are constant? Okay. So what is changing? So we understand that the amount of moles that we're adding, or the amount of moles is changing, right? We're adding more. We're adding more air into the ball. And as a result of that, we know that the volume will also change. So therefore we understand that this is Avogadro's law. Right? Because if the amount of gas in the soccer ball is increased, and then the volume will also increase. And we know that because that's what Avogadro states. And from here, we clearly see that there's a direct proportional relationship between the volume and the amount of gas or the amount of molecules, right? So here, let's draw an example. Again, let's do a particle diagram, right? Before, and let's do an after. Okay, that's good enough. So let's assume this is my air pump. Right. And then you kind of have the tube. Right, and then we're pumping in air. So then we have, let's say, we'll have 2 gas molecules. And then we'll have 3. Again, we want to make sure we stay true to the law of conservation of mass. So because we drew a total of 5 particles, we have to have 5 particles here. 1, 2, and then 3, 4, and then 5. So from this particle diagram and from the scenario, we can clearly see that as a result of adding more molecules into a system, right, into the soccer ball, we see that the volume will expand. And you see this day to day life, right? If you have a flat tire, you have to add more air to obviously inflate the tires. With the in this common scenario where with the soccer ball, you leave your soccer ball in you leave your soccer ball outside during a cold day. The soccer ball will deflate, and to inflate it, I mean, you could wait for it to be a hot day and leave it outside, and the volume will expand, right? And right, and we know that because of Charles' law, right? If you leave it outside, where with higher temperature, right, the volume will increase. It's that directly proportional relationship between temperature and volume. However, using Avogadro's law, we don't have to wait till the sun comes out or till temperatures increase to increase the volume of the soccer ball, but we can manually add more molecules of air into the soccer ball, and thereby increasing the volume and inflating the ball. I hope that makes sense. And if you need further clarification, you can look at my other videos I made for gas laws. And yeah, thank you for watching.